Okay, guys, so the second part of this lecture has to do with actually definitions of continuous functions. And the situation that I will be dealing with is this following: X and Y are metric spaces. E is a subset of a metric space X. Okay, now I have to make sure that this thing is clearly visible. Can you see it? Okay, hold on, give me a minute. This is better, right? And I have a function f that maps E into Y. Okay, so let P be a point in E. And now the first definition kind of sounds silly. Uh, the function f is called continuous at the point P. So this is kind of a little bit of a silly sounding statement, but that is the definition of the thing that I'm giving you. Uh, I don't seem to be able to position my paper well. Uh, so uh, the function f is called continuous at the point P if the limit of f of x as x approaches P is equal to the value of the function f at P. Okay, so let me say two things. That first of all, it involves the limit that we had in a previous half an hour. So this definition, on the one hand, asserts that this limit, as x approaches P, exists, and second of all, it is not just arbitrary limit, it is actually equal to the value f of P. So the idea here is that if I have a function not necessarily continuous, if f is not necessarily continuous, then this limit of f of x as x approaches P may not exist. For instance, if I have a function that looks like this, then at this particular point, 0, if p is equal to 0, then the limit does not exist. Well, why doesn't the limit exist? I'm just going to appeal to the theorem that we proved the last time. So I can choose a sequence xn, which converges to 0 on this part, on the left of 0, and then the limit of this f of xn, of the sequence f of xn, will be equal to, let's say this is 1. On the other hand, I can choose the sequence xn, which converges to 0 on this part, and then f of xn will converge to -1. And since the limit has to be unique, it cannot be two different values, this function is not continuous. In other words, this limit does not exist. I'm actually not telling you anything more than you should know from Calculus 1. Now, here is another example when the limit does exist, and this is very simple. So I'm going to take a function f. Yeah. For some reason, my papers don't seem to stay right for the camera. I'm going to take the following function. I'm going to take a function that looks like this. So it is just like a parabola up to 0, and then at this point, at the point 0, the value of the function is 1. Okay, so this is a function f of x, which is equal to x squared if x is not equal to 0, and equal to 1 if x is equal to 0. Okay, so let me take the points xn, which converge to 0. In that case, f of xn will converge to, so this function is x squared minus 1, I'm sorry. F of xn will converge to -1, and if it does it to the right, f of xn still converges to -1, and as you recall, the value of this function f at the point 0 doesn't matter. And so the result is that the limit exists, the limit of f of x as x converges to 0 exists and equal to -1, which is not equal to the value f at 0. So this, again, is not a continuous function, and this is one of the reasons why when we defined the limit, we had to mess with those things. Remember, we have to say that x is not equal to p and all this other stuff. So in principle, the value of f may not even be defined at the point p, but the limit may be defined. But for continuous function, as you will see in a second, it really doesn't matter. So let's go back to the definition. So here is the definition again. And I'm going kind of a little bit in the opposite direction from Rudin. On a test, you're welcome to give my definition, the definition from Rudin. F from E, a subset of a metric space X, into Y is continuous at the point P in E. If the limit of f of x as x approaches P exists and equal to f of P. Now, if you remember the definition of a limit, this means that for every epsilon greater than 0, there exists a delta greater than 0, such that if the distance from x to P is less than delta and greater than 0, there is this unpleasantness here, then the distance from f of x to f of P is less than epsilon. Okay. Now, what happens if x is equal to p? Well, if x is equal to p, then f of x is the same as f of p, and so this distance is equal to 0, and so it's automatically being less than epsilon. So for the sake of definition of continuity, we really don't need this being greater than epsilon. So here is the second definition of continuity. F is continuous with p if for every epsilon greater than 0, there exists a delta, which depends on epsilon greater than 0, such that if the distance from x to p is less than delta, that implies that the distance from f of x to f of p is less than epsilon. Okay. Let's redo this definition one more time. So what this means is, what is this? This is the neighborhood of P of radius delta, and this is the neighborhood of f of P of radius epsilon. And so this definition says, this is alternative definition, that f is continuous at P if for every neighborhood of f of P, there exists a neighborhood of P such that f maps this neighborhood of P into the neighborhood of f of P. In other words, and I hope I'm going to use the words that you're familiar with, if I take my function f and I apply it to the set n sub p, so this is not the value of a function. This is function applied to the set. This is the image of n sub p. So if I take f and apply it to this thing, it will be a subset on n f of p. Okay, and this is finally the definition of a continuous function at a given point. As I said before, the meaning of a definition of a function continuous at a point is a little bit ridiculous because it's really not what it means. Notice that I'm dealing with neighborhoods here, and so the reality is that what it means is that the function f is continuous at some neighborhood of the point p, but for some strange reason in mathematics, we say that the function f is continuous at p. So here's what it means. Here is the function, which is, and here is the point p. And what does it mean that this function is continuous at the point p? Well, let's take this value f of p, and again, I'm going to attempt to use a different color. I don't know if it will work or not. So for every very, very, very tiny itsy bitsy neighborhood of the value f of p, there exists an itsy bitsy neighborhood of p such that f maps every point of this neighborhood into the point of the neighborhood f of p, and this is definition of a continuous function at the point. Now, finally, let me say that uh, the function f from e to x, from e to y, is continuous on e if f is continuous at every point p in E. Okay, so this is a definition of a continuous function, and very, very quickly, because we studied limits before and we studied all this other stuff, we can prove a whole bunch of theorems. So let's suppose that I have two functions, f of x and g of x, and these functions f and g map the set E into Y, or this time let's do it E into R or C or even RK that I will do in a moment. Well, in that case, if f of x, if f and g are continuous on E, then f plus g is continuous on E. F times g is also continuous on E. And finally, f over g is continuous on E if f of p is not equal to 0 for any point p in E. Okay, well, so I don't know if I have to go through the proofs of it, but remember we proved that the limit of f of x plus g of x as x approaches p. So if f of x is continuous function, this is equal to f of p plus g of p. So the same result works for the sum of two functions, the same result works for the product of two functions, and the same result works for ratio of two functions, provided the second function is never, ever, ever being equal to 0. So as a result, we will quickly see that if I have functions f that maps, I don't know, say real numbers into real numbers, and if the function f of x is equal to x to the power n, then f of x equals to x is a continuous function. And so if I take the product of this continuous function with itself, I will have a continuous function. And so now if my function f of x is equal to the sum of ak x to the power k, k from 0 to n, remember I'm only allowed to deal with finite sums so far, then this is a sum of continuous functions times constants, which are also a continuous function. And so every polynomial is a continuous function. Okay, but there is a little bit more to it than that. So this time what I'm going to do is I'm going to assume that x, y, and z are three metric spaces, and I have a function f that maps x into y, and I will write it down this way. It is a little bit more convenient. And then I will have a function g, which maps y into z, and I can define what is called the composition of two functions. Uh, so the composition of these two functions is the function g composed with f, and this is a function from x into z. And the way this function is defined is g composed with f applied to x is equal to I apply f to x. So now my value of f of x is in y, and then I'm going to apply g to this. Now it is a little bit interesting, I think, in general, philosophically, that I'm taking the composition of functions f and g, and yet I'm writing it as g composed with f. So g comes on the left instead of f coming on the left. This is a necessary thing in mathematics because of this particular diagram. You probably see the same phenomena in, say, linear algebra. When you define the matrix, you expand the vector, and then the coefficients of the expansion becomes a column of the vectors of the matrix, not the row of the matrix. This is the same thing. When we're dealing with composition of functions, then even though f is the first function, g is the second, we're writing it as g composed with f. Well, guess what I have to do next? I have to prove a theorem, and the theorem will say that if f is continuous from x to y, and g is continuous from y to z, then the conclusion, of course, that the composition of these functions g composed with f is a continuous function as a function from x to z. Okay. Are you ready for a proof? So let me start with a new page here. I still cannot get used to the way this thing writes. So I'm taking a function f from x to y, and the function g from y to z. And then I have a composition of this function, g composed with f, which on x is defined as g of f of x. And this is a function from x to z. And I have to prove that this function is a continuous function. Okay, so what do I have to prove? I have to prove that for every point p in x, and for every neighborhood of g composed with f of p, there exists a neighborhood of p such that f composed with g maps this neighborhood of p into the neighborhood of n of g composed with f of p, or equivalently, what I have to prove is that for every epsilon greater than 0, there exists a delta depending on epsilon greater than 0, such that if the distance from x to p is less than delta, then the distance from f of g of f of g of x, no, g of f of x, I'm sorry, g of f of x to g of f of p is less than epsilon. Do you agree with me that this is what I have to prove? Okay, so let's start doing it one thing at a time. I mean, first of all, I know that f is a continuous function. And that means that for every epsilon greater than 0, there exists a number. This time, let me not call it delta. Let me call it, for instance, eta greater than 0, such that if the distance from x to p is less than eta, then the distance from f of x to f of p is less than epsilon. Agree? What I have done is I have written the definition of a continuous function, but instead of delta, I write eta. What difference does it make? Now, I also know that g is a continuous function, and in particular, it is a continuous function at this point q equals to f of p. Do you agree with me? So the conclusion, I will say that for a given eta, yeah, hold on a second. What? Yeah, so I'm sorry for the interruption. So given an eta and this point q, there exists a delta greater than 0, such that if the distance from, I don't know, y to q is less than delta, then the distance from g of y to g of q is less than epsilon. So if we combine these two statements together, we will have that for every epsilon greater than 0, there exists a delta greater than 0, such that what happens here is that if x, remember y is equal to g of x, so if the distance from x to p is less than delta, then this implies that the distance from f of x from from g of f of x composed with g of f of p is less than epsilon, and that implies that the composition of two continuous functions are continuous. Uh, okay, so let's see. What else do I want to prove here? I want to prove another very, very important theorem. And this is a theorem that deals with continuous functions. Again, f from a metric space x into a metric space y. And remember that in chapter 2, we studied all sorts of funny notions. Why does this paper not look very good? We studied all sorts of funny notions of open sets and closed sets, and of course, continuity of a function relates to those notions. Let me try to adjust the slide. Let me try it again. Okay, that seemed to be a little bit better. And here is a theorem which is very, very important. So I'll remind you that if I have a set A in X, then I can form an image of this set, f of A. And so this will be the set of all y in Y, such that y is equal to f of x for some x in A. So this is a notion, this is a definition of an image of a set. But now if I have a set B in Y, I also have something called an inverse image of B. So notice that the function f may not be invertible. So f minus 1 may not be an inverse function, but the set here is defined to be the set of all x and x, such that f of x belongs to the set B, and this is called an inverse image of a set. And the big theorem is that the function f from x to y is continuous if and only if for every open set V in Y, f minus 1 of V is an open set in X. So the function is oh, so the function f is continuous if and only if the inverse image of every open set is open. And in topology, for those of you who are taking topology or will be taking topology, this is a very important theorem because their neighborhoods are not available. And actually, when you take topology, this will be the definition of a continuous function. The definition of continuous function is a function that maps such that for every open set in Y, f minus 1 of V is an open set in X. So inverse image of an open set is open. The proof of this theorem should not be very difficult. So let's see what we're doing. So suppose that f is continuous first, and V is an open set in Y. Okay. So what I want to do is I want to prove that f minus 1 of V is open in X, which means that I want to prove that every point of this set, remember this is a set, that every point of the set is an interior point. So what does it mean? It means that I have to take a point x in f minus 1 of V. This is a set. And I want to say that there exists a neighborhood of this point x, which completely belongs to this f minus 1 of V. So if I take a point x, I know that f is continuous, f of x belongs to V. And I know that x is a continuous function, and therefore V is an open set. So I'm going to take an arbitrary neighborhood of this point f of x in V. Such neighborhood exists. I hope you agree with that, because V is open, and then there exists a neighborhood of x such that f maps this neighborhood of x into the neighborhood of f of x, which means what? Which means that this neighborhood of x, every point of this neighborhood, f maps into this neighborhood. In other words, this neighborhood of x have a property that f minus 1, that it belongs to f minus 1 of this n of f of x. So I took an arbitrary neighborhood in V, I apply the inverse image to this neighborhood, and I have a neighborhood n of x, which completely belongs to V. Now that means that V is open because for every x in V, I got a neighborhood which belongs to V. Well, the other way is just as simple, so it's just a repetition of this very, very same argument. If this is true, if the function f has a property that the inverse image of the set is open. That means that I have a function f from x to y, and I'm going to take an arbitrary point x in x. In that case, f of x is a point in y. So I'm going to take a neighborhood of this f of x, and the neighborhood of this f of x is a set in y, which is open. Are we good so far? We're almost done. And if this neighborhood of f of x is an open set, then I just don't seem to be able to fit the rest of this paper under the light. If the neighborhood of this f of x is an open set, then by assumption, the inverse image of this thing is open in x. And if it's open in x, and of course it contains x, then that means that there exists a neighborhood of x such that f maps the neighborhood of x into n of f of x, which by definition of a continuous function that you should be comfortable with right now is the same thing as the function f being continuous. Okay, just one more remark I see in Rudin here. So I'm going to make the same remark to you, that if I have a function f that maps, let's say, Rn or Rk into Rk, and I'm going to take another function g. Well, let's take a function f, and the function f of a point x will be defined as a norm of x. That's the way Rudin write it. I like to write it this way. And so I claim that this function is continuous. Well, to verify it, what do I have to do? I have to pick an arbitrary point x, okay? And I'm going to pick an arbitrary epsilon greater than 0. And so I'm going to look at, so what is true is this version of triangle inequality, that this quantity is less or equal than x minus y. And so what that means is that f of x minus f of y in absolute value is less than x minus y, or the distance from f of x to f of y is less than the distance from x to y. So what that means is that if I make sure, if I take an arbitrary epsilon, and I'm going to choose delta to be equal to epsilon, that means that the distance from x to y is less than epsilon, and that means that the distance from f of x to f of y is also less than epsilon. And that means that this function f is continuous as well. And that will finish the materials that you need to know for Tuesday. And on Thursday, I will start talking about continuous functions on compact sets. So this will be a much bigger topic. Bye. Ooh.